So draw a mechanism for a base catalyzed polymerization, of methyl alpha methacrylate to give the plexiglass polymer. By the way, that's as far as the dimer. All you need to do is just the dimer, because you don't have to go 10,000 of them. So remember, poly means as many as yeah. You could have essentially infinite, right? You could have a world-spanning polymer. Actually, there is a mountain-spanning polymer. There is a fungus that has enveloped an entire mountain and its surroundings, and some of those polymers reach like the length of a freaking mountain that is generated. Yeah, there's some really crazy stuff. By the way, one of the extinction events actually happened because of essentially what would have been the ancestor of fungi. They did a previous edition of this global warming thing, except they eliminated like 90% of all life on the planet. Yeah. Yeah. So we're not the only ones. Anyways. So we're doing we'll need to get this methyl alpha methacrylate, right? We'll need to write that out. That's what that looks like. Yay. This one is going to be a base catalyzed, and so we'll have to start the process with a base, right? Yes, OH minus, that's basic. Note, however, it being catalyzed by it means we have to do what? We have to regenerate the OH minus, right? Yeah. So if you catalyze something with a base, that means catalyzed means it doesn't get consumed, right? Means it regenerates at the end. Okay. So the first thing we're going to do is we have an OH minus. What would that do? That has an extra lone pair and a negative charge, doesn't it? Well, we have a double bond here. Probably going to be involved, right? What's special about these vinyl hydrogens? Vinyl hydrogens, meaning at the end of a double bond. Okay, so this double bond right here, because it's at the end of a chain, the hydrogens that are attached to it are much more acidic. Okay? They're significantly more acidic than, say, the CH3's hydrogens. Meaning the OH minus can take them, right? Okay, so it's going to give its electrons into a bond with that H. Yep. Well, not a carbocation, but a carbanion, right? Okay. So this spot right here, I'm sorry, not the H, the carbon. I'm sorry. This spot right here is going to have the OH attached to the carbon. That's going to leave a negative charge on that carbon right there. Okay? Because the negative charge is going to push the negative charge along. Okay, so that negative charge now is going to be reactive. It's now going to be a strong base, isn't it? Again, this spot, we know that spot on there can accept a negative charge, can't it? Okay, because we did that before. So our negative charge goes into a bond with this carbon that pushes the electrons over onto the next carbon. And guess what can continue happening? Yeah, you're going to have just another one of these monomers on there. You see that these are two of these monomers. This is the original right here. This is the second one over here. Okay. Everybody see that okay? And you reset. See that? You have that negative charge. So another one can come along. And then again, and again, and again, meaning the poly in polymer, right? When you finally end this, you would regenerate an OH minus. There you go. Cool, huh? Okay. That's polymers. That is a base catalyzed polymer. And most polymers, by the way, there's sort of two general groups of polymers. There's the addition ones that are going to involve a double or triple bond in addition to it. They can be acid catalyzed, like we just saw that acid reaction, similar to that. They can be base catalyzed, like we just did. And the other one is going to be the water addition, hydration reactions, and dehydration reactions. The dehydration reactions forming the polymer. The hydration reactions splitting apart. Yeah. And those are the ones we find the most in nature. Like, that's how you do things like proteins.
So polymers really just...
Yeah, proteins are polymers. This stuff on your head, we call hair, that's polymer.
So protein.
Keratin. Yeah. Or the horns on ram, also another polymer. That's why it's plastic-like. Yeah. It's not quite plastic, but you get the idea.
Yeah.
Similar.
Yeah.
Yep, your nails, same. Your proteins, same.
On that second box, what is that arrow coming off?
The arrow comes from this lone pair right here. You have a negative charge. That negative charge lone pair is going to react with this carbon.
Oh.
And then that's going to push the electrons in the double bond into a new negative lone pair.
Because that carbon method that's attacking is positive.
Yes, it's slightly positive. Yeah.
Not like, okay.
The resonance structure.
Okay.
Yeah. So this is slightly positive. One of the reasons you can use this compound to do this so readily is because this double bond can have a resonance structure where the double bond goes here between these two carbons, and then the oxygen accepts a negative charge. It has a slightly positive charge. Very slight, though. This is no ion. Yep. Still enough to allow a strong base, a strong negative charge center that's relatively small in size to be able to get in there to attack, to react with it. Okay. And keep in mind, if you have base in here, you need a fair concentration of the base for this reaction to go. The reason is, most of the times this pop on here, it's just going to come right off as OH minus again. Okay?
Why?
Because it's much less stable with the OH on here and as a carbanion, right? Despite the resonance structure that stabilized it. But if you have enough concentration, what's going to happen is you'll get this pop done temporarily, and you'll have it long enough, for one of these to come along and react with it. And then that, as long as we get rid of the carbanion, the polymer's stable. Okay?
Is that also maybe one there?
Mm-hmm. Yeah, it's another carbanion. Yeah, the negative is what's interrupting the bond right there. But yes, the projector is, not exactly the one easiest to read on a projector. Because I can zoom in, but yeah. Anyways, anybody else have any other questions on this?